Hi, my name's Ben Hardless. Welcome back to the ENM2600 playlist. Hopefully you enjoyed the last video on complex numbers. If you haven't watched it yet, please go back and check it out because it's kind of a prerequisite to what we're going to be doing here. So today I just want to do a quick video on Euler's formula. It really is written like it should sound like Euler, but apparently it's pronounced Euler. So we'll go with Euler. Anyway, in the last video we talked a bit about complex numbers and the different ways that we can express them. We talked about the different types of operations that you can do with them and how to actually go about doing that. And this time we're going to talk about a different way of expressing them, which I alluded to last time. So if we have a complex number, nice simple one, 1 plus j, right? And this is in Cartesian form. We can also express that in polar form, right, where we have some magnitude of z at some angle theta, and that would be the polar form, and we can do that, right? So 1 plus j, what's that going to be? It's going to be I calculated it before, so it's going to be √2 at an angle of pi on 4. So there we go. That's perfectly valid to express it like that in polar form or Cartesian form like this. So this is a nice neat one because we've got a nice fraction of pi here for the angle, which we can which is nice and easy to represent, right? We don't have a whole bunch of decimal places happening, and so this should indicate to you that we are definitely talking in terms of radians, right, not degrees. So if you're following along on your calculator, then just change it into rad mode and you'll be all sweet. So what is this Euler's formula business? Well, before we can get to that, we did also talk about one other way of expressing this complex number z, which was we could also express it in what is also a sort of a polar form as well. We can express it like this: the magnitude and multiply that by cosine of the angle, right, pi on 4, plus j sine of the angle, which is pi on 4. And this is the same thing. And if that's not clear to you, then I encourage you to go back and watch a previous video because we did work this out using a nice example, and we really dove into the depths of it. So this is cool. Well, what does that mean for us? So in a general way, we could say that a complex number b can be expressed as the magnitude of b multiplied by the cosine of the angle, which we'll just call theta 2 because we've already got theta up here. So that cosine of theta 2 plus sine, j sine rather, of theta 2, and that's sort of expressing it generally, right? Now Euler's formula is interesting because it is saying that, and you know what, instead of b I'm going to use r. Anyway, what we'll show is that we can actually express this yet another way, and this comes from the fact that e to the power of jx is equal to the cosine of x plus j sine of x. Now, where does this relationship come from? Well, and this is really Euler's formula, and so it deserves a bit of an asterisk, doesn't it? Now, where does this actually come from? Well, you know, it's a really long explanation that I frankly don't have time to do, but there's a really good explanation of it on Khan Academy. And where it really comes from is, I'll change color. There we go, that's better. Nice pinky sort of color. Where it comes from is if you actually take e to the x and you do the Taylor expansion, and I'm mindful that I haven't done a video on Taylor polynomial expansions yet, but that will come later. If you do a Taylor expansion on e to the x, you will find that it looks eerily similar to the Taylor expansion for cosine of x plus sine of x. So anyway, that's sort of, because we haven't covered Taylor expansions yet, I don't want to go about proving this, but that's really where this is coming from, this relationship. So wow, this is interesting. You know, if you change this x here and this x here and this x, and you change them to say theta 2, for example, right? Theta 2, theta 2, theta 2. That's this thing here, isn't it? That's this right here. So if we then substitute this e to the j theta 2 in for this part, couldn't we then say that this is equal to, you know, if we take this part and we sub it in for this, couldn't we then say that this is, you know, r is equal to the magnitude of r times e to the j theta 2? Well, absolutely we can. So you will see it, and usually it doesn't have the magnitude sign there because it's r for radius. So that's really cool, because, you know, and you might be thinking, well, how is that going to be useful to me? What does that actually mean in practical terms? Well, what it means in practical terms is that if we take if we decided to do something like if we wanted to, for example, square this whole thing, right? Where we said, hey, we're gonna do oh, that's not very bright, is it? I might get a brighter shade of green for us to work with. If we said, well, you know what, this r squared, we want to square r. Well, what does that mean? It means that we have to square this and we have to square this, doesn't it? And that's it. It's the same as doing this. Now, when you look at it in this polar form with the cosine theta 2 plus j sine theta 2, which is, you know, right around here, this bit here, that's a bit tricky, because you're like, oh, well, what do I do to square this? You know, I'm gonna have to do this like a squared plus b squared plus 2ab. Am I going to have to do that? And, you know, you could go about doing things that way, but when you express it in this form, you know, taking note of Euler's formula, it becomes really easy, because you have, you know, all you do is you say, well, this is going to be equal to, and I'll switch back to yellow, this is going to be equal to that squared, right, times e to the j theta 2 squared, which is going to be equal to magnitude of r squared. And you know, when this thing, all we're going to do is we're going to multiply these two things together, right, to get the new index term. So this is going to be e to the j 2 theta 2, right? So now that's really cool, because if we then convert back into the polar form, and I'll just bring us over here somewhere, right down this way. If we then convert back into the polar form, so it looks like, just erased by accident, it looks like this a bit again, then, you know, we're taking this and we're trying to put it in this form again. Well, that's nice and easy, because what we're going to have is magnitude of r squared, right? That's this bit here. And then we've got to sort out, well, what do we do with this bit here? And all we're going to do is put it back in that polar form. So it's going to be cosine of whatever this is, right? So it's 2 theta 2 plus j sine of the same thing, 2 theta 2. Now that's pretty interesting, isn't it? That's pretty cool. So what it means is, when we take complex numbers and we want to raise it to different powers, this form here is really useful. And we'll see in the next video that what we can do is really make use of this when we're taking the roots of complex numbers, because if you've got a complex number, and I'll go up into the top corner here, if we've got a complex number and we call it A, complex number A, and we want to raise that to, we want to take like the square root, just, you know, for argument's sake, just for ease of example. Okay, we want to take the square root of complex number A. What do? Well, that's an interesting one, because isn't that the same thing as raising the complex number A to the power of a half? It is indeed. So then couldn't we then say that this is going to be equal to the magnitude of A, the square root of that, right? And then multiply that by e to the j theta, and we'll call it theta 3, whatever that is, and over 2, because all we're doing is we're, you know, I haven't calculated out an angle, it's just, you know, so we're just calling it theta 3, right? But if we raise this to the power of a half, which is taking the square root of it, then we can just simply get rid of that and put the half in here, right? So it just becomes j theta 3 on 2, and then we can convert that back into polar form pretty readily. So hopefully that gives you a bit of an idea about Euler's formula and the beginnings of your understanding of how it might be useful. In the next video, we'll look into this a bit further. I hope you've enjoyed this. Thanks for your time.